Welcome, everyone, and a huge welcome, especially to you, the listener, to today's deep dive.
Glad to be here.
We have, a genuinely fascinating mission today. We are looking at a source document simply titled crankshaft.pdf.
Very to the point.
Right, exactly. Now, since you already follow the engineering space, you know that technical PDFs, dense bulleted lists, complex schematics, they're pretty much par for the course.
Oh, yeah.
You definitely don't need a primer on the basics of internal combustion. But our goal today is to take this highly technical source material and really drill down. We want to get into the granular, expert-level details it provides about what is essentially the mechanical heart of an engine.
Right.
We're going to examine the extreme tolerances, the forensic failure points, and just the sheer metallurgical stress this component endures. And I promise, even if you live and breathe this stuff, we are going to uncover some insights today that will make you look at a powertrain in a completely new light.
It's a remarkable document, really, because it presents such a stark contrast. On one hand, you have this very sterile, two-dimensional schematic, perfectly dimensioned, perfectly labeled. But then on the other hand, the text outlines the chaotic, high-pressure, incredibly violent reality of what this component actually has to survive.
It's brutal.
It really is.
Yeah.
It's a perfect candidate for a deep dive because the text doesn't just give us the anatomy. It details the precise functional tolerances and provides this forensic breakdown of what happens when the physics finally win and things go disastrously wrong.
Exactly. It's like looking at the blueprints for a mechanical cardiovascular system, but with all the failure modes explicitly mapped out. Okay, let's unpack this. Let's start by visualizing the specific anatomy detailed in the source. Because you, the listener, don't have this document right in front of you.
Right. Painting the picture is key here.
Yeah. So the PDF kicks off with a highly detailed cross-sectional diagram of a crankshaft. It's a massive, heavy-duty, complex piece of metal. It is not just a straight rotational axis. It's a series of staggered, interconnected segments. It honestly looks like a geometric metal spine.
A geometric metal spine. That is an incredibly accurate way to frame it. And the document gives us the exact nomenclature to map that spine out.
Right.
It points out the main journals, which are the primary axis points where the shaft rests and rotates within the engine block's main bearings. And then offset from that central axis, we have the rod journals.
That's where the connecting rods actually meet to the shaft.
Exactly.
And connecting those main journals to the offset rod journals are the webs. The diagram shows them as these thick, solid plates of metal bridging the spatial gaps between the rotational center and the offset throws. Looking toward the front end of the diagram, the source explicitly labels the front shaft, which leads directly into a gear, and then finally a keyway.
Right, the keyway.
Yeah, that precision-cut slot in the shaft. It's designed to lock a mating component, like a harmonic balancer or timing gear, into place so it spins in absolute perfect synchronization with the shaft itself.
We also have to look closely at the surfaces engineered specifically for managing friction. Fluid retention, lateral movement.
The diagram points those out too?
Yeah, it points out the seal surface on the end, which is critical for oil retention.
Yeah.
And the thrust faces machined onto the sides of the webs.
Those are super important.
Vital. Because a crankshaft isn't just dealing with rotational and downward force, it's dealing with longitudinal movement, sideways forces that literally try to push the shaft right out of the block. We also see the journal sidewall, and importantly, the bearing width surfaces,
which dictate exactly how much surface area is actively riding on the hydrodynamic oil film of the bearings.
Spot on.
And then there are the fillets. The diagram highlights these small, curved transitions where the flat sections of the webs meet the cylindrical sections of the journals. It's fascinating how a seemingly straightforward schematic quickly turns into a highly specialized map of stress management zones.
Oh, absolutely.
But getting into the finer details, there were two specific features on this diagram that really stood out when we were reviewing the source.
Yes, these were the elements that elevate the document from a standard parts diagram to a real engineering study. First, the diagram specifically points out a lightning hole bored directly through the center of one of the rod journals.
A literal hole right through the center.
Right. Think about the physical physics at play there. You have this massive, heavy-duty piece of forged or billet steel that has to endure immense explosive loads. But simultaneously, engineers are carving out material from its core to reduce the rotating mass.
Wow.
It's a masterclass in managing the polar moment of inertia. You're finding that absolute knife-edge balance between maintaining structural rigidity and reducing the parasitic loss of spinning excess weight.
It's brilliant engineering. You need the tensile strength of a bank vault, but you need it to spin with the least amount of resistance possible.
Exactly.
But what's the second detail that stood out to you?
It's the internal plumbing. What's fascinating here is that this solid piece of metal is actually a highly engineered system with its own complex internal fluid dynamics.
The oil holes.
Yes, the diagram points out oil holes drilled precisely through the journals to supply the bearings. But right next to them, it labels a very specific oil thrower surface. And here's the truly striking part. The diagram includes a highly specific restrictive note right next to that label.
Right.
It says this particular oil thrower surface is for a, quote, 6.25-inch bore only, unquote.
But why 6.25 inches specifically? I mean, when you see a tolerance or a design restriction that tight in a source document, it really makes you pause. If an engineer is designing an oil thrower surface, what happens if that engine's bore is, say, 6 inches or 6.5?
It comes down to the precise velocity and volume of the oil being sheared and thrown by the rotational mass. It's interacting with the specific geometry of the crankcase. The sweep of the connecting rod, the distance the oil have to travel to lubricate the cylinder walls or cool the underside of the piston, all of that is calculated based on the bore size.
So it's perfectly calibrated.
Exactly. That note tells us that the fluid dynamics are so finely tuned that changing the cylinder bore by a fraction of an inch renders this specific oil thrower design mathematically suboptimal, or even entirely ineffective.
That level of specificity is incredible. It proves that this isn't just a generic modular hunk of steel that you can drop into any block.
No, not at all.
Every millimeter, every angle, and every fluid channel is custom tailored to operate in a singular, highly specific environment.
It forces us to view the crankshaft not just as a passive lever, but as a dynamic, active participant in the engine's thermodynamic and fluid management systems.
Which transitions perfectly into the functional analysis provided in the source material. The text explicitly lists out the 6 core functions of a crankshaft. And I'd love for us to dig into this list because understanding the functional requirements really contextualizes the extreme stress this component is under.
Let's do it.
Function number 1 is listed simply as convert reciprocating to rotary motion.
While that sounds like a fundamental mechanical definition, the kinetic energy transfer involved is staggering. We're talking about taking thousands of violent linear impacts per minute and converting them into a perfectly smooth, continuous rotational force.
It's the ultimate magic trick of the engine.
It really is. The crankshaft is the translator for that kinetic energy, and it has to perform that translation without shearing apart under the alternating stress cycles.
That sets up the next 2 functions perfectly. They are listed as carry heavy bending, torsional, and thrust loads, and deliver pressurized oil to main and rod bearings. Putting those 2 side by side reveals a massive engineering contradiction.
It's an immense juxtaposition. On one hand, you have the structural integrity required to carry those loads. Torsional loads means the shaft is literally twisting along its axis every time a cylinder fires, while the resistance of the drivetrain fights back from the flywheel end.
Right.
Bending loads means the downward force is trying to snap the shaft between the main bearings. It is enduring constant, brutal physical distortion. But while it's twisting and bending on a microscopic level, it must simultaneously act as a delicate, highly precise delivery system for pressurized oil through those tiny drilled channels.
Because if that delicate oil delivery system fails for even a fraction of a second, the hydrodynamic film collapses. The pressurized oil doesn't reach the main and rod bearings, metal touches metal, and the friction will weld the entire mechanism together and destroy the engine almost instantly.
Exactly.
It's performing brute force, high torque labor while simultaneously executing microscopic fluid management.
And that operational reality explains the next 3 functions listed in the text. Provide bearing with hardware-resistant surface, deliver power to gears and flywheel, and provide sealing surface for oil seals. When you synthesize those, the crankshaft emerges as the ultimate middleman of the powertrain.
Taking the power, enduring the friction, keeping the oil sealed, and passing the energy onto the flywheel, it has to provide that hardware-resistant surface because it's enduring that constant high-speed friction against the bearings.
Right.
And from a metallurgical standpoint, that usually means the journals are hardened, maybe induction hardened or nitrided, while the core of the shaft remains relatively ductile to handle the bending and twisting without shattering. It's providing the sealing surface to keep all that pressurized oil inside the block. And after taking all the punishment, it takes the harnessed energy and delivers it out to the gears and the flywheel.
Every single peripheral system relies on this central hub playing its part flawlessly. If the surface hardness fails, the bearings wipe. If the seal surface is scored, you lose oil pressure. If it can't deliver the power cleanly to the flywheel, the engine tears itself apart from vibration.
Here's where it gets really interesting. The source document doesn't just detail how the component works in a vacuum. It actually dives into the troubleshooting and maintenance protocols.
The detective work.
Exactly. It takes us into the realm of engine forensics. Because when a massive, perfectly engineered system like this goes wrong, it leaves clues.
And the text gives a highly specific checklist for that forensic work. When engineers are examining a damaged crankshaft, the document explicitly states they must first look for cracks at fillet radii and oil holes.
Which connects directly back to the anatomy we mapped out earlier. The fillets, those curved transitions at the webs, and the drilled oil holes. Why are those specific geometries the primary suspects for cracking?
Because in mechanical engineering and metallurgy, those areas act as massive stress concentrators. A sharp corner or a drilled hole disrupts the uniform flow of stress lines through the metal.
I
When the
see.
shaft bends and twists under the torsional loads we just discussed, the stress accumulates at those specific geometric interruptions. The notch sensitivity of the metal means that if a fatigue crack is going to propagate, it's almost always going to start at the fillet radius or the edge of an oil hole.
Wow.
The very features that allow the crankshaft to function, the complex offset geometry and the internal oil channels, are mathematically its greatest vulnerabilities.
That makes perfect sense. But the forensic clues, the document lists, go even deeper into the mechanics of assembly. The text specifically mentions looking for a slipped shrink fit, and it gives the instruction to check witness marks. For those analyzing a failure, what exactly are they looking for when they check a witness mark?
In high-stress mechanical assemblies, a witness mark is a physical, readable clue left behind by a failure, a shift, or a sudden misalignment. When parts are mated together using a shrink fit, where a larger component is heated so it expands, fitted over a shaft, and then cooled so it clamps down with immense pressure, they are theoretically immovable.
Right.
But if the torsional load exceeds the friction of that shrink fit, and the parts slip even a millimeter, they leave evidence.
So engineers are literally reading the metal.
Precisely. They are looking for microgalling, a microscopic scratch, a change in the wear pattern, or even a slight shift in the alignment of the metal grain. Those witness marks prove exactly what shifted, in what direction, and often imply the magnitude of the force that caused it.
But the document also briefly mentions the need to check bearings and check for misalignment, right?
Yes, because a misaligned block will force the crankshaft to bend slightly with every rotation, which inevitably leads to a fatigue failure at those fillet radii.
But the major focal point in this troubleshooting section, the failure mode the document spends the most time breaking down, is the threat of something called ovality. Now, ovality sounds exactly like what it is, a perfectly round journal becoming oval-shaped over time, but the text provides a highly technical breakdown of the exact vector forces that cause it.
It does, and the mechanics of ovality are a perfect study in applied physics. According to the document, ovality is caused by the combination of two specific factors: a reduced effectiveness of the lubricating oil paired with the directional thrust of the connecting rod.
And it gets incredibly precise here regarding the geometry of that thrust. The text highlights that the maximum directional thrust from the connecting rod happens somewhere around 45 degrees after TDC.
Top dead center.
Right. Now, since you, the listener, know engine timing, you know top dead center is the peak of the piston stroke. But why does the text pinpoint 45 degrees after that point as the moment of maximum destructive force?
It's all about vector geometry and combustion pressures. At exact top dead center, the combustion pressure is immense, but the connecting rod is perfectly straight up and down. The force is pushing straight down into the main bearings. But as the crankshaft rotates past TDC, the angle of the connecting rod becomes more severe.
Okay.
By the time it hits approximately 45 degrees after TDC, you have a massive confluence of forces. The cylinder pressure is still incredibly high from the expanding gases, but now the rod is at a steep angle.
So instead of just pushing down, it's pushing hard sideways against the journal.
Exactly. The lateral vector force is maximized. It's delivering its absolute peak, punishing directional thrust against one specific side of the rod journal. And if your hydrodynamic oil film is compromised or less effective at that exact millisecond, that repetitive, severe directional thrust pounds the hardened steel. Over millions of cycles, it literally wears the perfectly round rod journal into an oval shape.
Which introduces clearances that shouldn't exist, dropping oil pressure further, causing catastrophic vibration, and eventually knocking the engine to pieces. But the text doesn't just present the problem. It gives us the engineering solution and the exact tolerance for ovality. It states that, generally, the maximum ovality that can be carried is in the region 1/4 the working clearance of the bearing.
Think about the microscopic reality of that tolerance. We are dealing with massive steel forgings, managing thousands of pounds of force, and the failure point is measured in fractions of a bearing's working clearance. A standard working clearance might be 2 or 3 thousandths of an inch. A quarter of that is less than a thousandth of an inch.
Wow.
The tolerance for ovality is often a fraction of the thickness of a human hair.
And when it exceeds that, the text says it can be recovered by grinding, which means pulling the entire rotating assembly out of the block, putting it on a specialized lathe, and precisely shaving away the high spots of the oval until the journal is perfectly round again.
But of course, grinding it perfectly round means the overall diameter of the journal is now smaller. You then have to use thicker, oversized bearings to compensate for the lost material and reestablish that critical working clearance. It's a highly delicate recovery process that impacts the long-term balance and oil flow characteristics of the entire engine.
Which brings us to the final piece of source material we have for today's deep dive. And this is where the entire scale of everything we've been discussing gets completely turned on its head.
The visual evidence provided at the end of the document is staggering.
It really is. Up until now, looking at the initial diagram talking about fractions of thousandths of an inch in working clearances, you might be picturing a crankshaft from a standard automotive V8 or maybe a heavy-duty diesel truck. But the document includes a striking photograph that shatters that assumption. Since you can't see it, I'll describe it. The photo shows a man physically positioned inside the curves of a crankshaft. The component is so massive that the technician is dwarfed by it, and he is in the middle of fitting these pink belt-like heating elements completely around one of the massive crank pins.
What's fascinating here is, well, if we connect this to the bigger picture, this image completely recontextualizes the deep dive. We aren't just talking about a small car part. The photo shows a piece of machinery so massive that a human is positioned inside its curves. This isn't an automotive application. This is a piece of machinery so unimaginably massive, likely from a marine or industrial power generation application, that a human being looks like a mechanic working inside a steel canyon.
And the caption for the photo specifically states that the technician is fitting heating elements around a crank pin during the Wärtsilä treatment process.
Wärtsilä is highly renowned for building some of the largest, most powerful, low-speed marine and energy engines on the planet. Seeing that specific name explains the massive scale, but the process itself is what's truly fascinating. When you're dealing with a crankshaft of that magnitude one that weighs dozens of tons and handles the power output of a small municipal power plant, you aren't just unbolting parts.
Right, you're dealing with metallurgy on a macro scale. Those heating elements he's fitting around the crank pin are inducing massive thermal expansion.
Exactly. To assemble or disassemble a component with a shrink fit at that scale, or to relieve the immense internal stresses within the forged steel, you have to precisely manipulate the temperature of the metal. The technician is manually applying specific thermal treatments to expand the crank pin, either to mate it to a web or to alter its metallurgical grain structure.
It brings the human element right back into the center of this massive, automated, industrial reality. Despite the immense size, despite the digital precision of the engineering, it still requires delicate, hands-on human intervention. An engineer has to physically climb into the machinery, wrap specialized thermal elements around the steel, and monitor the conductive heat transfer. It's a stunning contrast to the neat, sterile, two-dimensional diagram we started with.
It perfectly encapsulates the dual nature of high-level engineering. You have the theoretical geometry on the page calculating the exact polar moment of inertia for a lightning hole, or mapping the fluid shear for a 6.25-inch bore oil thrower. But eventually, that theoretical math has to survive the sweaty, heavy physical reality of extreme temperatures, torsional twisting, and millions of explosive cycles.
So what does this all mean? We started this deep dive looking at a highly technical PDF document, analyzing diagrams, bulleted lists, and rigid mechanical nomenclature. What we actually unpacked was a story of extreme forces, precise engineering, and massive scale.
We really did.
We examine how a geometric metal spine acts as a kinetic translator, absorbing explosive linear forces and converting them into continuous rotational power. We look at the inherent contradictions of a component that must carry brutal torsional and bending loads while simultaneously acting as a delicate, pressurized fluid delivery system.
Hmm.
We decoded the forensics of failure, understanding how stress concentrators at fillet radii and the sheer vector force of a connecting rod at 45 degrees past TDC can pound hardened steel out of round. And finally, we saw how even the most massive multi-ton marine components still rely on the precise physical application of thermal dynamics by human hands. It's a testament to the incredible sophistication hidden inside the machinery that powers the industrial world. I think this knowledge changes the way you'll think about the everyday machines operating all around us.
This raises an important question, one that goes beyond the specific mechanics of a powertrain. I want to go back to the concepts of witness marks and ovality that we explored in the forensic section of the text. We discussed how immense repetitive directional forces, specifically that localized lateral thrust, at exactly 45 degrees after top dead center, gradually reshape even the hardest, most wear-resistant steel.
Right.
If the lubrication or the environment fails even slightly, the invisible cyclical stress leaves a visible, permanent, and readable history on the metal. I'd like you to ponder how that concept applies to the broader physical world. How do immense repetitive forces, whether they are mechanical vibrations, environmental pressures, or even structural loads, gradually reshape the hardened foundations around us? How does invisible continuous stress eventually leave its own readable witness marks on the structures and systems we rely on every single day?
That is a phenomenal thought to leave on. The invisible stress leaving visible, permanent marks. Thank you so much for joining us on this deep dive. We'll catch you next time.